Okay, everyone, good evening. Thanks for Prof. Chen's introduction. I'm very glad to be here to share our paper published in FEM last year. As Chen just introduced, the topic is direct energy rebound effect for road transportation in China. Let's start. The transport sector accounted for 26.24% of global energy consumption and about 24% of carbon dioxide emissions related to fossil fuels in 2022. But in 2021, this share is only about 20%. Globally, the energy consumption of the transport sector is mainly attributed to road transportation, accounting for about 80%. Energy demand in transport rose by 4% in 2022 as it continued to rebound towards pre-COVID levels. Now have a look at the figure 2. By 2030, the share of oil in road transport energy demand drops from 92% today to 88% in the stated policy scenario, that is STEPS, 84% in the announced pledge scenario, that is APS, and 78% in the net zero emissions by 2019. So in China, the total energy consumption in 2021 reached 5.26 billion tons of standard coal, with transportation contributing about 8.35% to the overall energy consumption. So transportation is one of China's major sources of energy-related carbon dioxide emissions. With ongoing industrialization and urbanization, the demand for energy within the transport sector is poised for further expansion. In pursuit of energy saving and environmental sustainability, now the Chinese government, of course, have done a lot to enhance energy utilization in road transportation. For example, the Ministry of Transport issued the guidance on building of a low carbon transportation system in 2011. The objective, of course, is to try to improve transportation system efficiency. In 2019, the release and implementation of the energy efficiency and the carbon dioxide emissions intensity grades and evaluation methods for operating passenger cars or trucks is also emerged as a robust mechanism for regulating vehicle operations. Also try to improve energy efficiency and control the greenhouse gas emissions. Then in 2021, the Ministry of Transport introduced the Green Transportation 14.5 Development Plan in 2021. So this imposes additional requirements to improve energy efficiency or to reduce energy intensity. So till now, a substantial body of literatures have tried to find the effectiveness of energy efficiency improvement in saving energy and reducing carbon dioxide emissions. But it is worth noting that improving energy efficiency often results a decreased per unit energy service costs, of course. So the load cost of energy services may stimulate increased demand for these services. So the projected energy savings stemming from energy efficiency improvement may not utilize the fully. So this phenomenon is named as the rebound effect. Now we can take an example. Enhanced energy efficiency may reduce the per kilometer travel cost for these cars, but as well as incentive great car usage. So this additionally demand for consumption could lead to a failure to attain the expected reduction in energy consumption. Now, how to explore the potential magnitude of energy rebound effect is especially important in the formulation of the policies designed to control energy consumption in the road transportation area. From the theory, the concept of rebound effect can be traced back to the book. It's a very classic book. The core question together, here is the equations. Together with the utility maximization and the dual expenditure minimization problems, the mechanism of the rebound effect for N commodities can be illustrated within these 4-in-1 graphs as provided here. Now, the figure A here is price effect and the rebound effect. The figure B can show the own price effect, and it can be used to calculate the direct rebound effect, and also can get the consumer surplus increase. C, of course, is conversion graph, and the D, we can use this to analyze the cross price effect. Now, this is to calculate indirect rebound effect and also the consumer surplus increase. Here in this, our paper, we focus on direct rebound effect. Now here, E/0 denotes the initial energy efficiency level, and E/1 is the raised energy efficiency. Of course, E/1 is larger than E/0. When energy efficiency rises, that is, energy consumption demand remain constant. So the anticipated energy saving is E0 minus E1. As energy efficiency increases, energy demand shifts from S1 to from S0 to S1. So here lead to the corresponding energy savings, that is E0 to E1. The portion represented by E minus E1, so can show the expected energy savings, but remains unrealized due to the upswing in energy demand. To measure the energy rebound effect, one very widely used approach here is energy service demand attributable to energy efficiency. That is the first one, eta E/S. So S represents energy services. E is corresponding energy consumption, and energy efficiency, that is E/0 equals S divided E. So E/0 eta E here indicates the elasticity of energy consumption concerning energy efficiency. In the empirical research, always it's not so easy to get the sufficient data set of variable energy efficiency. So the direct energy rebound effect can be always obtained by the response of energy services demand to variations in the price of energy services. That is eta PS as the equation 2. Given the data pertaining to energy service prices here, PS are more easily available comparing to energy efficiency data. Here, Formula 3 is more widely used in empirical research than Formula 2. Formula 4 here, energy prices are considered exogenous variables, and energy service demand is solely influenced by energy service price. So energy service price here determine energy efficiency and the prices. So when energy efficiency remains constant, the energy rebound effect can be expressed by the elasticity of energy use concerning energy price, that is equation 3. Yeah. And the ADAPES is also widely used as a measure of direct energy rebound effect in some fields, always when the unavailability of the date for energy use within distinct segments, like China's transportation industry, also absence of energy efficiency data. So here we choose the ADAPES to calculate the direct energy rebound effect in this paper. Now, energy rebound effect can be characterized into various outcomes, like backfire effect if RE is larger than 1, just equal 1, it is named full rebound. Larger than 0, smaller than 1 is partial rebound, and 0 rebounds or in the super conversation effect is these cases we really want to, right? Okay, now this is for our research. The load transportation is divided into 2 categories: load passenger transportation and load freight transportation. These 2 subsectors exhibit the varying operational mechanism and are driven by distinct factors leading to different responses when they face the improvement in energy efficiency. Here, given the absence of efficient annual average vehicle mileage data in China, so we use the passenger turnover as a metric indicator for energy services in road passenger transportation. Passenger turnover is contingent on both the number of passengers transported and the transportation distance. Researchers, of course, have indicator except of the vehicle mileage and other energy services in road passenger are influenced by such as energy prices, income levels, and urbanization rates. For the load freight, here, load freight transportation, we use the freight transportation turnover as energy service indicator. Load freight transportation here is mainly influenced by energy price, industrial structure, and the scale of commodity transportations. In our paper, we applied the double logarithmic model to investigate the rebound effect both in road passenger transportation and road freight transportation. Now, this is the equations for the 2 sectors. Then we decompose the fuel price. This is also the innovative point of our paper. We try to decompose them into 3 components: the sequence of the highest fuel price sequence, Pmax, the cumulative decrease in fuel price, P cut, and the left, the cumulative rebound in fuel prices, that is PIC. Now, these are the decomposition models, where the coefficient of P cut is just considered as energy rebound effect. Here is the figure just to show this figure just to show the trend of fuel prices after the decomposition. The trend of highest fuel price series aligns closely with that of the original fuel price series. That means China's fuel prices have generally exhibited year-on-year growth. Now, the cumulative recovery fuel price series and the cumulative falling fuel prices series remained comparatively stable during the initial period. This period corresponds to the upward trend in fuel prices. So overall, we can see China experienced more frequent increases than decreases in fuel prices. This is the time period from 2000 to 2018. And then we construct, with the time series data, we construct a short round panel error correction model, includes a lag term to illustrate the correction mechanism. there is a short-run deviation from the long-run equilibrium state. So the magnitude of the error correction value signifies its capacity to correct deviations from the long-term equilibrium state. Now, these are the equations. The difference sequence of each variable, of course, mean the short-term fraction of variables. I think all of you are maybe very familiar with that. To boost the reliability of the test outcomes, this study employs the typical LLC test, IPS test, and HT test to assess the stability of each variable in the load passenger transportation equation. Now, this table, table 1 shows the specific panel unit route test results. From here we can see, except for log P max, the original sequence of all variables fails to reject non-hypothesis of possessing a panel unit route. So these findings indicate that each variable in load passenger transportation is characterized by a first order integrated sequences, and the variable displays a co-integration relationship. So we employ this method to assess the co-integration among the variables in load passenger transportation. These tables show the specific outcomes of the test. To mitigate the impact of the heteroscedasticity, we utilized a comprehensive generalized least squares method to conduct a panel co-integration regression for the load passenger transportation equation. Now, this table shows the results of long-term co-integration equation. It's very obvious that the long-term energy rebound effect for China's road passenger transportation stands at 15.7%. Especially the LERE is the lowest in Eastern China at 12.6%. And the highest in Western China at 25.4%. So these results imply that over the long term, energy efficiency policy have been effective. And the energy savings resulting from improved energy efficiency have not been completely offset by the energy rebound effect. As well, there exists a positive relationship between the cumulative recovery of fuel prices and the demand for energy services in load passenger transportation of the long time. Also, other variables like the growth of per capita has significantly positive effect, and the urbanization the same. This slide is about short-term energy rebound effect, that is SERE. SERE for road passenger transportation is calculated 41%. That means in the short term, the actual energy savings achieved by China's road passenger transportation were only 100 minus 41. That it's 59% of the expected energy savings resulting from improved energy efficiency. Also, they varied different regions, like the lowest SERE was found in Central China at 36%. In comparison, the SERE generally for road passenger transportation was greater than LERE, but didn't reach the level of a backfire effect. This is for load freight transportation, similar to the stability test conducted for the variables. So here we can skip them. Also, yes, we apply 3-panel co-integration test methods, or 3 tests reject non-hypothesis. So we can, using the elasticity of load freight transportation turnover to fuel prices as measurement index for energy rebound effect. Here is the long-term energy rebound effect for the load freight transportation. Now the data here is the value is 48.3%. Within this estimation, the LERE in Central China was the lowest at 14%, while Western China much higher. The highest one is 40.6%. Now, we can find no matter which area, the LERE didn't reach the level of a backfire effect, that is rebound factor larger than 1. No, didn't reach. So that means energy savings resulting from improvements in energy efficiency here in load freight sector was not completely offset by the presence of ERE. Much more, we can find when we consider the regression coefficient of the total retail sales of consumer goods, the results we can find that they show a significant positive effect in the long term. Also shows the growth of total retail sales of consumer goods have a substantial positive impact on the road freight transportation turnover time. The regression coefficient of industry structure show the output value of the secondary industry promotes the turnover of road freight. We also found, yes, with the elasticity of road freight transportation turnover to fuel price, we also found that SERE for road freight transportation. Here is the value is 23.3%, is generally lower than the LERE for road freight transportation. Regarding the cumulative recovery of fuel prices in the short term, there is a simultaneous increase in fuel prices and the road freight transportation turnover. So the short-term fluctuations in the total retail sales of consumer goods have positive effect on road freight transportation turnover. That's very similar with the long-term effect. And the industrial structure is also similar, has positive effects. Then we did the robust test for training the time window widers. The results show that we adjusted the time window to cover the years from 2004 to 2018. And these are the SERE and LERE date. We can find they observed also observed a partial rebound effect without reaching the level of backfire effect. Also did the robust test for excluding some special samples. Here we assess the robustness that the benchmark regression results. Yes. Now, just a short conclusion of the paper, that is China. Here's road transportation sector exhibits a noteworthy energy rebound effect, especially the long-term energy rebound effect for road passenger transportation and road freight transportation range from 13 to 25 and 14 to 48%. Road passenger transportation and road freight transportation show differentiation responses to improvement in energy efficiency, no matter in short run or long run. And the ERE, whether at the national or sub-region level, the ERE is observed in road passenger transportation and road freight transportation. They don't reach the level of backfire. This is very lucky. The rise in fuel prices has not substantially impeded the growth of energy services in road passenger transportation and road freight transportation. Also, a study, of course, can get several policy implications, like enhancing energy efficiency, of course, will remain the primary end view for achieving energy saving and consequent reduction in emissions. within the road transportation sector. The rise in fuel prices has not effectively covered the demand for energy services in road transportation, both in short and long term. Also, we suggest other emission reduction policies, like may establish more stringent fuel efficiency stands for long-term truck options, or maybe can increase the tax rate for the road passenger transportation in the short term. Yeah, okay, this is our paper. Now, our recent publications about rebound effect in different areas, like household rebound effect. We also extend direct rebound effect to indirect rebound effect. Also extend to, this paper is about energy rebound effect. We extend to carbon rebound effect. And also we explore the relationship between a rebound effect and the welfare effect. Yeah. So if you are interested in this topic, maybe looking forward to collab with you. Now this is my speech. Thanks very much. Thanks for your time.